Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
So every single day, the internet expands by exactly 2.5 quintillion bytes of data.
Which is just, an absolutely massive number to even wrap your head around.
Right, it's huge. And if today we have, say, 550 quintillion bytes, tomorrow we have 552.5, and then the day after that, 555. It's like this relentless mathematical heartbeat.
Yeah, it really is.
And today, our mission for this deep dive is to basically decode the hidden patterns that are driving that massive, highly predictable growth.
Because it's the kind of consistency that feels almost impossible, right? Especially when you consider how chaotic the internet actually seems on the surface.
Oh, totally.
But underneath all those, cat videos and articles and data transfers, there is a very strict, elegant mathematical architecture holding the whole thing together.
And to help us unpack that architecture, we're diving into section 3.0 of chapter 3 from Contemporary Mathematics.
A fantastic section.
Yeah, it really is. And for this deep dive, since we're really pulling apart the underlying mechanics of these concepts, I'm going to playfully adopt the role of the student today.
I love that.
Right. I'll just be throwing the questions your way on behalf of everyone listening, and you can be our resident lecturer, guiding us through the machinery of how these patterns actually operate in the real world.
Well, I will gladly take on the lecturer mantle.
Yeah.
But fair warning, this isn't just about abstract numbers on a chalkboard.
Okay.
The mathematical patterns in section 3.0, they govern everything from how global server farms scale up to handle that internet data to, how you intuitively build a retirement fund.
Wait, really?
Oh, yeah. Or even how you physically condition your body to run a marathon.
Okay. That is exactly the kind of shortcut to being well-informed that we are looking for. So let's jump right into the foundation of it all. We are dealing with what the textbook calls arithmetic sequences.
Yes, arithmetic sequences.
But before we start, using formulas to predict the future of the internet, I feel like we need to understand the anatomy of the pattern itself. What exactly separates an arithmetic sequence from just a random string of numbers?
Well, so the foundational concept is just a sequence, right?
Yeah.
Which in mathematics is really nothing more than a list of numbers in a specific order.
Okay.
Each individual number inside that list is called a term. So you have your first term, your second term, your third term, and so on.
Makes sense.
And we usually denote these with a lowercase a and a subscript number indicating its position. So a sub 1 is your starting point.
Right. So if I look at my historical grades in my last few assignments, and they are, say, 90, 85, 95, 80, that is technically a sequence.
Yes, exactly. It's a list of terms in order.
But there's no real predictability there, right?
That's...
It's just reacting to how much I studied that week. So what upgrades a standard sequence into an actual arithmetic sequence?
What makes it specifically arithmetic is the presence of a constant difference.
A constant difference.
Right. And in formulas, we denote this with a lowercase d. For a sequence to be arithmetic, the terms must increase, or decrease for that matter, by the exact same fixed, non-zero number every single time.
Oh, I see.
The gap between any two consecutive terms is always identical. There are no sudden leaps, and there are no unpredictable drops.
It makes me think of a metronome.
Yeah.
Or, a steady heartbeat. Tick, tick, tick. It's this relentless, unchanging pace that drives the whole sequence forward.
That is a great way to look at it.
Because if the heartbeat skips or changes rhythm, like my unpredictable assignment grades, it's not arithmetic anymore.
That heartbeat analogy is perfectly aligned with how the math actually functions. Think about a simple example from the textbook. The numbers 7, 15, 23, 31, 39, and so on.
Okay, let me test the heartbeat there. Going from 7 to 15 means adding 8.
Right.
From 15 to 23 is adding 8. From 23 to 31 is adding 8.
Exactly.
So the constant difference, our d, is a positive 8. It never fluctuates. And because it never fluctuates, we have total predictability.
And predictability is the ultimate goal here. Humans crave a linear understanding of the world because it allows us to plan. If you know you are adding exactly 8 units of something every single time, you can project into the future.
But let's interrogate that projection for a second. Because counting term by term like we just did, that's totally fine for a short list.
Sure.
If I just need to know the next 2 or 3 numbers in that sequence, I can keep adding 8 in my head. But what if we need to know what happens way down the line?
Right, the distant future.
Yeah. If we are planning the infrastructure for a massive data center based on that 2.5 quintillion bytes of daily growth, we don't want to sit there adding the daily rate by hand 1,000 times to see where we'll be in 3 years.
No, you definitely do not.
There has to be a mathematical shortcut, right? to fast forward.
Absolutely.
Yeah.
Mathematics is, at its core, really the science of finding those shortcuts. And to fast forward into the future of any arithmetic sequence, we use a tool called the ith term formula.
The ith term.
Yeah. It allows you to pinpoint the exact value of any term at any specific position, which we just call position I, without having to calculate all the tedious steps in between.
Okay, so if I want to know the 100th term, my I is 100. If I want the 500th term, I is 500. So how do we actually construct this shortcut? Let's use a tangible example to build the logic. Say we have a sequence that starts at 4 and then goes 7, 10, 13. And we need to find the value of the 47th term.
Okay, let's break down the components you already know. You have your starting line, which is your first term, a sub 1. In this case, that's 4.
Right.
And you have your heartbeat, your constant difference. Since it moves from 4 to 7 to 10, you're consistently adding 3.
Okay, so starting point is 4, heartbeat is 3. And we want the 47th position. Now, if I am trying to build this formula intuitively, my instinct as a student is to just take that heartbeat of 3, multiply it by the 47 positions I want to find, and then add it to my starting line.
Which is a very common instinct.
But I know there's a critical trap there. The actual formula uses I minus 1, doesn't it? It tells us to multiply the heartbeat by 46, not 47.
Yes, it does.
Why did we subtract 1 from our target position? That always confused me.
That is probably the most common conceptual hurdle when projecting linear growth. Think about the physical reality of what you are mapping. You are standing on the starting line.
Okay.
That starting line is your first term, the number 4. You don't have to take a step to get to the starting line. You are already there. You inherently possess that initial value at position 1.
Ah, right. It's almost like a zero indexing problem in computer science. I don't add the heartbeat to the first term to get the first term.
Exactly.
The first term just simply exists as the foundation.
You got it. You only start adding the constant difference. You only take a step when you transition to the second term.
Oh, okay.
So to arrive at the second term, you take 1 step. To arrive at the third term, you take 2 steps. Therefore, to arrive at the 47th term, you only need to take 46 steps away from your starting position.
That structural logic is brilliant. Okay, so if we run those numbers, we take 46 steps, and each step has a value of 3. 46 multiplied by 3 gives us a total growth of 138. We add that accumulated growth of 138 to our starting foundation of 4, and we arrive precisely at 142.
Spot on.
The 47th term is 142, and we didn't have to calculate the 45 numbers in between to find it.
And that exact same logic is how engineers project data center needs years in advance. They take the starting capacity, calculate the steps forward using that constant difference of data accumulation, and instantly know the future requirements.
That is incredibly satisfying to just skip to the end like that. Now, that covers projecting forward from day 1, but let's look at a different reality, because often we don't have perfect data.
That's very true in the real world.
Right. We don't always get to see the starting line, and we don't always know the heartbeat right away. What if we just, drop into the middle of a timeline?
Like dropping into the middle of a movie.
Exactly. Say we are forensic accountants or data analysts, and we only have 2 random, disconnected snapshots of information. Can we reverse engineer the entire architecture of an arithmetic sequence from just 2 points?
We can, provided we know the growth is genuinely linear and arithmetic. This is actually a fundamental technique in data analysis.
Really?
Oh yeah. If you have any 2 terms in an arithmetic sequence, you possess all the genetic material required to clone the entire timeline, past and future.
Okay, let's test this detective work.
Yeah.
Imagine we are looking at a company's historical server usage. A lot of the early records were lost. We don't know what they started with in month 1.
Okay.
But we do have the logs for month 7, where they used 56 terabytes of data. And we have the logs for month 19, where they used 104 terabytes. That is all the info we have.
Month 7 is 56, month 19 is 104.
Exactly. How do we reconstruct the heartbeat from that fragmented data?
The mechanism to find the constant difference here relies on a simple ratio. It is the total change in value divided by the total change in position.
Change in value over change in position. Okay, let's look at the value first. We went from 56 terabytes up to 104 terabytes. That is a total physical increase of 48 terabytes.
And how much positional time elapsed to create that growth?
We moved from month 7 to month 19. That is a span of 12 months. So it took 12 positional steps to generate 48 terabytes of growth.
Which leads you directly to the constant difference. If a system grows by 48 units over exactly 12 equal steps, You simply divide 48 by 12.
Which gives us 4. The heartbeat is 4.
There you go.
They were adding exactly 4 terabytes of data every single month. We just unearthed the date's value.
And once you have unearthed that heartbeat, reconstructing the missing task is trivial. You just put the machinery in reverse. So how do you find the starting line, the A sub 1, now that you know the rhythm?
Well, if I am standing at month 7, holding 56 terabytes, and I know every step backwards reduces the load by forward, I just need to take 6 steps backward to arrive at month 1.
Right.
6 steps backward at 4 terabytes a step is 24 terabytes of reversed growth. I subtract that 24 from my month 7 value of 56, and I get 32. They started with exactly 32 terabytes in month 1.
Beautiful.
You don't need the whole ledger, you just need the trajectory.
And that reverse engineering is profoundly useful. Whether you are analyzing a competitor's fragmented quarterly reports or trying to extrapolate ancient climate data from ice cores, if the underlying mechanism is arithmetic, 2 data points give you the keys to the entire timeline.
Okay, so we've mastered pinpointing specific moments in time, both predicting the future and unearthing the past. But there is a totally different way we interact with linear growth, isn't there?
Yes, there is.
Often, we don't just care about what a value is on one specific day. We care about the total accumulated weight of the entire sequence.
Exactly. You don't just want to know how many gigabytes of data were uploaded on January 15th. You want to know the total sum of all data uploaded over the entire month to ensure your servers don't crash.
Or like, if I'm training for a race, I don't just want to know that I am running 10 miles on week 6. I want to know the total accumulated mileage I've put on my running shoes over the whole 6 weeks so I know when to replace them.
Right. Practical applications.
So how do we calculate the sum of a finite arithmetic sequence? And by finite, I mean it has a defined beginning and end.
So to understand the summation formula, we actually have to look back to the late 1700s, to a famous historical anecdote about a young German schoolboy named Carl Friedrich Gauss.
Oh, I've heard of him.
Yeah, legendary mathematician. The story goes that Gauss's teacher, wanting an hour of peace and quiet, instructed the classroom to add up every single integer from 1 to 100.
Which sounds like an absolute nightmare of brute force mental arithmetic.
Right.
Like 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. You'd be carrying numbers for an hour, inevitably making a mistake somewhere around like 68.
And the teacher expected exactly that. But Gauss walked up to the teacher's desk mere seconds later with the correct answer, which was 50-50.
Wow. In seconds.
In seconds. He didn't sit there adding term by term. He fundamentally recognized the underlying symmetry of an arithmetic sequence.
He visualized the architecture. I've always loved the mental model for this. If you imagine all the numbers from 1 to 100 written in a long line on a ribbon.
Yes, the ribbon model.
Yeah, and you take that ribbon and fold it perfectly in half, you are pairing up the opposite ends of the sequence. So the very first number, 1, aligns with the very last number, 100, adding up to 101.
Exactly.
And the second number, 2, aligns with the second to last number, 99, which also adds up to 101.
And because an arithmetic sequence have that steady, unyielding heartbeat, every single pair moving inward will perfectly balance out to that exact same sum. You don't have 100 individual numbers anymore. You just have 50 pairs of 101.
Which is incredibly elegant. 50 times 101 is 50-50. He just bypassed the tedious addition by recognizing that the sequence balances itself.
And that childhood realization is the exact basis for the summation formula we use today. To find the sum of any finite arithmetic sequence, you take the total number of terms, let's call it n, and you multiply it by the average of the first and last terms.
Okay, so n times the average.
Right. Mathematically, it's an n multiplied by the quantity of the first term plus the last term divided by 2. It's just Gauss's ribbon trick formalized.
It is brilliant. Okay, so we now have a remarkably powerful toolkit. We can project future terms, we can reverse engineer starting points, we can calculate massive accumulations instantly.
We can do it all.
Let's take these tools out of the abstract and apply them to human behavior. Section 3.0 has some fantastic real-world application exercises that really highlight how deeply this math governs our daily lives.
Oh, totally. Applications of arithmetic sequences emerge anywhere. A quantity increases by a fixed amount at each step. The textbook provides scenarios that mirror really common human endeavors.
Like what?
Well, there's a chess player named Jordan committing to adding 30 minutes of practice every week.
Yeah.
A recent graduate named Christina increasing her weekly savings deposits by $5 every week. A runner named Jasmine adding 2 miles to her training schedule every single week.
What strikes me about grouping all these scenarios together is that they are all fundamentally about the mathematics of habit building.
Oh, that's a great observation.
Right. If you have ever set a New Year's resolution to incrementally read more pages of a book every night, or, lift slightly heavier weights at the gym each week. You are literally living inside an arithmetic sequence. It is the math of steady, reliable human discipline.
It is. And the reason these incremental habits are so powerful is because human psychology often fails to grasp the sheer volume of accumulation that the summation formula proves.
What do you mean?
Well, let's look closely at Christina's savings plan. She starts small, saving just $10 the first week. Her heartbeat, her constant difference, is increasing that deposit by just $5 each subsequent week. It feels like a minor, manageable change.
But if we apply our formulas to that minor change over a 52-week year, the results are staggering. First, if we want to know what her final deposit looks like in week 52, we use our isotherm shortcut.
Right, let's run the numbers.
We take 51 steps from the starting line, multiplied by that $5 heartbeat, which is $255 of growth. We add the starting $10, meaning in week 52 alone, her single weekly deposit has grown to $265.
Which is a solid deposit. But then, if you apply Gauss's ribbon trick, the summation formula, to find out the total accumulated wealth over that entire year.
Okay, let's do it.
You take 52 weeks, multiplied by the average of her first $10 deposit and her last $265 deposit.
Okay, so the average of 10 and 265 is 137.5. So 52 weeks multiplied by 137.5. That is an accumulated total of $7,150 saved in a single year, all born from a $10 start and a $5 incremental habit.
Exactly.
The linear progression completely masks a massive accumulated result. It's why financial advisors constantly preach the gospel of steady incremental investments.
The math proves that consistency is far more powerful than intensity.
Yeah.
But, just as you feel you've mastered this predictable linear world of arithmetic sequences, just as you feel comfortable with this reliable heartbeat of human progress, Section 3.10 throws a curveball in a section aptly titled, Who Knew?
Oh, I love a good structural pivot. We've spent this entire time praising the steady, unchanging, constant difference. So what disrupts the metronome?
The author points out a pretty profound truth. While human-engineered systems, like bank accounts, data centers, and marathon schedules, rely on arithmetic sequences, the natural universe largely rejects them.
Oh, really?
Yeah, not everything grows by a constant difference. Enter the Fibonacci sequence.
Fibonacci. Even if you aren't mathematically inclined, you've likely heard that name referenced in documentaries about art, architecture, or biology. It holds this almost mythical status.
It does, and for good reason. The Fibonacci sequence abandons the concept of a constant heartbeat entirely. Its rule is recursive.
Recursive.
Yes, meaning every term is generated by adding the previous two terms together. It starts simply with 1 and 1. The sum of those is 2.
Then 1 plus 2 is 3, 2 plus 3 is 5, then 8, 13, 21, 34, 55, and so on. It compounds on itself.
Exactly.
It doesn't walk at a steady pace. It begins to run, and then it launches into this exponential explosion.
And what the textbook highlights is where we find this compounding mathematical blueprint. We don't find it in our engineered spreadsheets. We find it woven into the fabric of nature.
Like where?
The Fibonacci sequence dictates the spiraling arrangement of seeds in a sunflower head. It determines the number of petals on various flowers. It governs the geometry of nautilus shells, the sweeping arms of galaxy spirals, and heavily informs the golden ratio used in classical architecture to mimic natural beauty.
The textbook even notes its presence in modern pop culture, mentioning how the rock band Tool meticulously utilized the Fibonacci sequence to structure the time signatures and syllabic patterns in their song Lateralus.
Oh yeah, that's a great example.
Once you are aware of the sequence, you start seeing its fingerprints everywhere.
It reveals a fascinating dichotomy. It is the underlying blueprint for natural organic growth, standing in stark contrast to the rigid linear growth we humans tend to engineer for ourselves.
Which brings me to a final philosophical thought I want to leave everyone listening with today. As we wrap up this deep dive, take a moment to mull over the tension between these two mathematical realities. Think about all of our human-made goals, our savings plans, our workout routines, our corporate projections for internet data storage. They all rely on the neat, predictable comfort of arithmetic sequences. We crave that steady +5 +2 +8 heartbeat because our minds have a limited cognitive load. We need linearity to feel in control of the future.
That makes total sense.
But the universe, The universe, with its infinite processing power, prefers the compounding self-referential spiral of the Fibonacci sequence. It doesn't add a constant. It builds entirely on its own past, compounding outward into galaxies and sunflowers. So why do you think human minds are so deeply comforted by the steady arithmetic heartbeat, while nature itself thrives in the wild exponential spiral of Fibonacci? By trying to force our lives into purely linear paths, are we somehow fighting the fundamental mathematics of nature?
That is a very profound question to end on. We spend our lives engineering arithmetic predictability in a universe designed for exponential chaos.
Something for you to think about the next time you marvel at a sunflower, or simply check the steady progress of your bank account. Thank you for joining us on this deep dive into the hidden mathematics of growth. Go out there, look closely, and start finding the hidden sequences in your own life. We will see you next time.